Our final topic is going to be angular momentum. Angular momentum is really important to our universe. Angular momentum is the rotational analog to linear momentum, and we represent angular momentum as a capital letter L. Angular momentum L is equal to the moment of inertia times omega. But let me show you where angular momentum comes from. Remember that we said that the sum of the torques equals I alpha. That's our rotational equivalent of Newton's second law. So this is equal to, well, I times alpha. What is alpha? You can also think about alpha as your change in angular speed over your change in time. That's how alpha is defined, our angular acceleration, okay? Now, our moment of inertia isn't always constant. It might change depending on what you do to your system. But we could write this as the change in the moment of inertia times omega divided by delta t. So this is equal to the change in our angular momentum over the change in time. So we can say that the sum of our torques has to equal the change in our angular momentum of a system over some time period. Then if we have no external torques in our system, so the sum of torques is equal to 0, then we can say that 0 is equal to our change in angular momentum over time. Okay, well, this is essentially saying that 0 is equal to our change in angular momentum. Now we can write the change in angular momentum as the angular momentum at some final point minus our angular momentum at some initial point, and that is equal to 0. So what this boils down to is that if we have no external torques acting on our system, and the system is, let's say it's expanding or it's spinning, we can say that the final angular momentum of our system is equal to the initial angular momentum of our system. And we see this happening all the time in our universe. This conservation of angular momentum, this is conservation of angular momentum, just like conservation of energy, where the angular momentum has to remain constant in time, or where the energy has to remain constant in time. We see this all the time in our universe. It's happening in our solar system. It's happening in galaxies. It's happening when a skater spins, when she holds her arms out, she's moving at some angular speed. She brings her arms in, she changes her moment of inertia, but the angular momentum has to remain constant. So when she decreases her moment of inertia by bringing her arms in, she ends up spinning faster. So her final angular momentum is faster. I'm going to demonstrate here conservation of angular momentum. So I have my stool here that spins, and I have two masses that I'm going to move further away from me, further away from the rotational center, and closer to me, closer to the rotational center, and you're going to see what happens. This whole time, angular momentum is conserved. Okay, so here I go. I'm going to start spinning, okay, and watch what happens when I put my arms out and then bring them back in again. If I'm conserving my angular momentum, that means that the mass of these objects times their velocity around the circle times their distance away from the circle must be the same, must be conserved at all times. And so the mass of these bodies are not changing, but I am changing their distance away from the rotational center. So the closer they are to the rotational center, the faster they're going to be moving around the circle. And the further they are away from the rotational center, the slower they're going to be moving away from the circle. And if my angular momentum is conserved, I'm going to reduce my orbital velocity, how fast these masses are moving around the circle when I move them in and out. Okay? So that's the conservation of angular momentum. Whether the masses are here or here, the angular momentum is the same, but I can change the orbital speed of these masses around the circle depending on how far away I move them from the center of my rotational axis. Okay, let's do it again. Slow down, bring them back in closer to me, spin them up. This is just like an ice skater. When she brings her arms closer into her body, she spins much faster. When she moves her arms further out, she spins slower. Okay, that's conservation of angular momentum. Just like what's happening in our solar system, planets that are closer to the rotational center are going to be moving around with the faster orbital speed, and planets that are further away from the rotational center are going to be moving around with a slower orbital speed, but the whole time their angular momentum remains the same. Here we're going to apply conservation of angular momentum to a piece of playground equipment, to a merry-go-round. And hopefully you were able to play on merry-go-rounds as a kid. I know that as we get older, a lot of times they start to remove some of the fun, more dangerous pieces of equipment. So here we have a merry-go-round, which we can model as a disc of mass 100 kilograms and a radius of 2 meters. And it's rotating with an angular speed, omega, about its central axis. Now, we're going to have a person, and they're going to jump on the end here of our rotating disc, of our merry-go-round. And that person has a mass of 60 kilograms. So after a person of mass 60 kilograms jumps onto the merry-go-round, the system's angular speed is 2 radians per second. So I'm going to call that omega initial. If the person walks slowly from the edge toward the center, find the angular speed of the system when our person reaches 0.5 meters from the center. So we're going to find the final angular speed of our system once that person walks from the end of the merry-go-round into the center at a distance of 0.5 meters away from the center. So I used to do this too when I was a kid playing on the merry-go-round. Run in toward the center and then run out from the center. It changes the speed at which you are able to rotate the system with some angular speed around the center. So we need to find our final angular speed when she moves in toward the center. So to do that, we have to use conservation of angular momentum. And remember that angular momentum initial has to equal the final angular momentum if we're doing conservation of angular momentum. Angular momentum is our moment of inertia times our angular speed. So the initial angular momentum we can write as the initial moment of inertia times the initial angular speed equals the final angular momentum times the final angular speed. And we're trying to solve it for WF, omega sub f, so we'll go ahead and do that. Omega sub f is equal to initial moment of inertia times the initial angular speed over the final moment of inertia. So we know the initial angular speed, 2 radians per second. We just have to figure out what here are the initial angular momentums of our system and the final angular momentum of the system. So I'll do that over here. The initial angular momentum of our entire system is going to be the angular momentum of the disk plus the angular momentum of the person when the person is out here at the end of the merry-go-round. So the angular momentum for a disk rotating about a central axis is 1/2 times its mass times its radius squared. And then we can assume that this person is like a point mass rotating on the end, on the edge of this disk. And so their moment of inertia is just going to be their mass of the person, times their distance away from the center of the axis, which in this case is way out here at the end of the merry-go-round. So that's the full 2 meters here. So we've got our initial moment of inertia of the system is 1/2 times the mass of the disk, 100 kilograms, times the radius of the disk, 2 meters squared, plus the mass of the person, 60 kilograms, times their distance out here to start with, which was 2 meters squared. Okay, and so then that equals, this first term is 200 kilogram time meter squared. So the unit of moment of inertia is kilogram time meter squared, plus the initial moment of inertia of this person out at the end is 60 times 2 squared, so 240 kilogram times meter squared. And so the sum of those gives us 440 kilogram time meter squared, okay? So that's our initial moment of inertia. For the final moment of inertia, we've got the moment of inertia of the disk, which remains unchanged, plus the moment of inertia of the person, which is different because now they've moved from the edge of our disk into a place where they're 0.5 meters away. So their new moment of inertia is going to be 60 kilograms, their mass, times their new distance away from the center squared. Okay, and so then that's going to equal the 200 kilogram meter squared plus this new moment of inertia turns out to be, I'm running out of room here, this turns out to be 15 kilogram time meter squared, which 60 times 0.5 squared. So then this is 200 kilogram meter squared plus 15 kilogram meters squared. So the final moment of inertia of the system is 215 kilogram meter squared. So now I can finish this. So our final angular speed is equal to our initial moment of inertia, 440 kilogram meters squared, times our initial angular speed, 2 radians per second, divided by our final moment of inertia, 215 kilogram meters squared. Okay? So our kilogram meter squared cancels on top and bottom. So our final moment of inertia of the system is 4.09 radians per second. So when we conserve angular momentum, whenever this person walks from the edge of the merry-go-round toward the center, they end up actually spinning up the system. The angular speed increases of this disk as it's rotating.